Okay, we are now recording. We'll start the slideshow from the current slide. And before we get started on this, let's discover what we're going to be doing. I think we can finish this chapter in the hour and a half, which we got left. I think we probably will even have time to move on to chapter 4. Because I don't think it's going to take us an hour and a half to do what we've got to do here. But then at 3:30, we will proceed to the lab. Now, I've got the labs copied, but I don't have the equipment set up because there was a class in that room and I wasn't able to get to it to set up. It's not going to be a huge setup today, but it's going to take a little bit of time to do so. Also, we will not be in 253. We'll be across the hall in 252. The lab we're doing today needs a longer run than what we have on those little hexagonal tables that we have in 253, so we'll be in 252. Okay, and then I also have the test run out all for you too, so when we finish the chapter and the lab, then I'll give you your test. So if you do have to leave early or something today, don't leave here without the lab and your test. Okay. We're at any questions before we get started today? Excuse me. We're on example 3.2, some stranded explorers. An Alaskan rescue plane, that's what you see at the top here. I'll get my pen out. Up here. Okay. Let me get my pen activated in the darker color. Alaskan rescue plane drops a package of emergency rations to stranded hikers, as shown here. The plane is traveling horizontally at 40 meters per second at a height of 100 meters. So you see that. Neglect air resistance. The first part, A, where does the package strike the ground relative to the point at which it was released? So relative to this point here, of course it's in the air there, but on the ground down here, how far over does it strike the ground? Okay? Where would you start a problem such as this? The last thing we did last time was some of your problem-solving strategies for projectile motion. That's what we're going to put into effect here. Where and how would you begin? Tell me something to do. I'll do anything you tell me. Well, within limits. Okay.
First thing I'll do is write down everything I know.
What's that?
First thing I'll do is write down everything I know.
Okay. And what else does the problem tell you that we haven't got written yet?
Gravity errors.
Ah, very good. And what is that?
9.8 meters per second squared.
Okay. Pointed.
9.8.
Yeah, pointing. Pointing.
Down.
Downward. Okay. So we have here, now they like to change colors. I'm not going to do it here. Here is the acceleration in the y direction, which is minus g, which is minus 9.8 meters per second squared. Excellent thing to add here. Now, the other thing for the A part here, where does the package hit the ground relative? So basically what we're looking for is x. This is the unknown here that we're searching in the A part of this problem. Okay, and you just gave us another quantity we didn't have. Anything else that we know or can assume where do we go from here?
Could you know a free body diagram?
Okay, and what do you mean by that? What would you do?
Describes all the forces that are acting on the plane.
Okay, you're doing chapter 4. Okay, all right. I can tell you've done this kind of stuff before. We don't really need to know forces so much now as just the motion, okay? I understand what you're saying, but how would you apply that here? And sort of a second part of what you said, if I understood you correctly, besides saying that essence had gotten here, okay, got that part. I thought you said on the plane. Okay, is the plane really the issue here? No, it's the package. You don't see the package, but it's dropped from the plane and going down. The plane's just going to keep on trucking, not going into the picture anymore. It's just sort of the launch site. So, what are some other things we might note here? How about some initial conditions? What would they be? Initial velocity? In which direction?
Going to the right.
Second?
Just going to the right. Well, I said X.
Okay, in the x direction. So what is your v, x? I like to call it I. The book likes O. It doesn't matter. What is that?
40.
40. Okay, all your velocity, 40.0 meters per second. So I could have just put v sub xi here, and would have saved a little bit of room because I might need this room for writing. Okay? Any others?
The y velocity.
Okay.
0.
You're right. V sub yi is equal to 0 because we're assuming the plane is in level flight. So when it drops the package, dropping meaning not throwing it, then it would have an initial velocity in the y direction of 0, but because the plane's moving at 40 meters per second, so would the package be. Okay, very good. Okay, based on this, then, are we ready to try to identify or locate a, let's see, what do they call them? The equations, kinematic equation. Of course, we want to mark Ryan here first before we locate that. What would be some? We're wanting to know x sub, let's just call this x final, okay? And if we're calling that x final, then this x initial would be 0. Let's just pick that as our orientation here. This is position 0, relative to there, where does the package fall? So that's going to be our x and final. Do we have a kinematic equation that addresses x final? And in this case, you might want to turn back a page or two and see. I do see one right off the top. On page 62, I see a delta x, which is exactly what we're doing relative to where it was dropped. What is that change of x? Anyone see that? (3.6b). Can I give any more hints? Okay. Anybody? Earth to class, come in please. Okay. Anyone locate equation 3.6b? One of the kinematic equations, as I said, on page 62, at least in this text. If you have a different text, it may be somewhere else. It starts with delta x, which is exactly what this problem is asking for. Any help on it? Second? Okay, v sub 0, I'm going to call it v sub xi. That's what I've been calling it. That's the same thing they are. Times, how about t? Did you say t? Okay. Plus 1/2 a, and that's a sub x, and, whoops, I'm in the wrong one. Yeah, there it is, t squared. Looked promising to begin with. Do we have a problem, Houston? Say again? We don't know the time. We don't know t. We've got v sub x. Now, we didn't say what a sub x was. What is it? A sub x. It's 0. Okay, we can write that down too. A sub x is equal to 0 throughout. Okay, but we don't know time. So maybe that wasn't our best check. Ah, excellent. Okay, how about that one? That's 3.6c. V sub x squared, that's the final velocity, is equal to v sub 0, well, I've been calling it x sub I. I'm just trying to keep mine square. Ooh, goodness gracious, where did that go? There we go. V sub x squared plus 2 a sub x delta x. But what's wrong with that picture? Yeah, this is 0, so we lose our delta x. So that doesn't do us any good. So those are the only two kinematic equations that have a delta x in them. This one we can't possibly use, so we must need something else. Say again? Okay, we need to do something in y. What is it we need in this one? T. We need the time. So is there a y kinematic equation that can give us the time? Second? Which one? This one?
Yes.
Here? Yeah. Yeah. Okay, let's try that one. Delta y is equal to what?
100.
Okay, that's your, well, okay, let me back off then. Okay. This would be y final then, not delta y. Delta y is y final minus y initial. In our case here, y initial is this thing, right? And we didn't identify this, we should have. This is our y initial, right? And what's our y final going to be? 0, okay. Or, we could do it the other way too, but this is keeping plus up positive, which is usually what we do, especially if we have acceleration due to gravity being negative downward. We've got to be consistent with it, okay? So, I'm going to rewrite this one ever so slightly, the way you said it. Y final would be 0. Well, I'll write down the kinematic equation first, and then we'll plug. Okay. Y final is equal to y initial. What else? Yeah, okay. V sub y initial t. But why did you leave it out? You left that term out. Why? Yeah, that's 0, so it was correct to leave it out. Plus 1/2 a sub y. And what is your a sub y? Okay, negative, which means this should then be a minus sign. See, if we're choosing negative downward, we have to be consistent with that. 9.8 t squared. Okay. And that's what we're looking for is the t. We've got all the other values. Y final is 0, y initial is 100. Okay? So we can write down everything right now. So I'm going to, if it's okay, move this quadratic term to the other side. okay? Because I like to start with the plus. 1/2 of 9.8 is 1/2 of 9.8, 4.9. T squared is equal to 100. Do you buy that? Yeah. Okay. It's cheap. Okay. So what do we do?
Solve for the t.
How?
By dividing 100 by 4.9.
Do it.
Do the square root.
And then take a square root. Sock it to it. 100 divided by 49, and take the square root of that. .51 seconds. Huh? Second? 4.52. Okay. I'm okay with that. Here's the reason. If you notice the rest of our problem, that has 3 significant digits. This, I don't know if they allow us to do 9.80 or that has to be 9.8. We can imagine that's 3 significant zeros. So I doubt if planes fly at exactly 100 meters plus or minus 1 meter. You know, I doubt if they're precise, but if we are going to do that, then let's have at least 3 digits there. At least some of the other things look like they could be 3 digits precision. Okay. Now, when you take a square root, should you do plus or minus? Except that
There's no minus sign.
yeah, we're not going to use negative times, you know. So we're going to be very happy with that. So now that we have the t here, we can now calculate the delta x there, because that's all we needed. We knew the v sub xi, we knew a sub x. I think we can do it. Okay, so let's use that next equation. That's why let's come up over here. The delta x is what we're looking for, and that's equal to what? Which is? 40. Okay, 40.0. I'll put the units in. Meters per second times what was our time? 4.52 seconds. Okay, and the seconds will go out because they've been dating. No, I'm just kidding. Okay, the AX 0. So we don't have anything in the last term. This should give you your delta x. And what does that come up being? Say again? 180.7. 180.7? Let's make it 181. 3 digits. Approximately 181 meters. Okay? Let's see how the book did. Oh, look at them. They got it right too. All right. So that's the A part. Where does the package strike the ground relative to the point of release? That's basically defining our delta x. The B part. What are the horizontal and vertical components of the velocity of the package just before it hits the ground? So we want V sub x final and V sub y final, just before it hit the ground. Anyone want to volunteer how to get either of those? Final velocity in the x direction, final velocity in the y direction. Anybody?
VF equals VI plus AT upon Y.
Oh, okay. You're doing the y part. So let's do that.
Well, the X one's going to be the same as...
All right. Okay. He was a hard worker. He wanted to do the hard one first. I'm lazy. Vx never changes. 40.0 meters per second, because there's nothing. We've assumed no negligible air resistance, so therefore the Vx never changes. There's nothing to change it. There's no, if we don't have air resistance, there is absolutely nothing, no forces that are retarding or speeding that up. Okay, and then what was your other statement?
The other statement is you need to find VYF.
Okay, VYF is equal to VIY plus AT. Okay, what was your VIY?
VIY is
0. Okay, so that's gone. What was your A sub Y, by the way, that was?
That was -9.8.
Negative 9.8 meters per second squared. And what was your time? 4.52 seconds. Pretty exciting, isn't it? Okay. And one of these seconds will cancel out. And what does that leave you with? 44.3 approximately. About 44.3 meters per second. Negative. Downward. Okay, of course it would be. It's falling down, so its velocity is down. So let's see how they did. They got 40 meters per second for the horizontal. That was tough. And negative 44.3 for the vertical. That was good. Now, the C part says, what was the angle of impact? We're looking for basically this angle right here. Now, I'm not saying their drawing is all that great, but that's the angle we're looking for. Okay? What would help us determine that angle?
Draw a triangle with the 181, that's the X, and 100 is the Y.
That triangle?
Yeah.
Okay. That would be an approximation, but you see the actual path is not this way, it's that way, right? So that's not going to quite give it to us. That would be a reasonable approximation, but not quite going to get us there. Okay. I wanted to if you would allow, here was your V sub x. V sub x final is 40.0 meters per second. And the V sub y final was downward, and that was 44.3. V sub y final is equal to 44.3 meters per second down. Now, if I extended the wrong line, sorry. I was going with your line, okay. Extended, and again, their drawing may not be, in fact, it isn't all that great, but if that is your angle, it's an angle like this too, right? This was your total velocity in that direction, right? Wouldn't the angle here have to equal the angle there? Those are called opposite angles. And you see if you had the V sub y here identified as this and the V sub x identified as that, what does that tell you? Since that's so crowded over there, let me extend this here. V sub x final equal 40.0 meters per second. Okay. V sub y final is equal to 44.3 meters per second. Okay. That's going to produce a, here would be your final velocity, which we really don't care about, but it's there. And wouldn't this angle be the same as your impact angle? Well, let's see. this angle here be the same as that one? That's a question. Yeah. So how could knowing the legs, I got to get my eraser off before I erase something I don't want to, the legs of that right triangle give you anything about this angle in the right triangle? Let's name those legs for me. Compared to that angle, this is the opposite, this is the adjacent. We know opposite and adjacent. Tangent function. And how would that be? It would be tangent of theta is equal to okay, that would be opposite, so that would be 40, 44.3. Okay, I would use a calculator to do that. Okay, be sure you're in, well, you could be, I think they're probably going to look for the answer in degrees, they are. So you tell me
46.8.
40 what?
46.8.
How do you get that?
40 divided by 44.3 and the tangent, inverse tangent of it.
Inverse tangent? You did?
Yeah.
Okay.
Find the angle.
Okay. Me. Okay, sorry. Okay, sorry about that. I drew it poorly. And I thought it kept looking bad, and I didn't wonder why. It's this angle. Sorry about this, team. That's the opposite angle from that one. Wait. I'm sorry, that's what I just had. That's not the opposite angle from that one. Okay? This is the opposite angle. It's this angle here, this angle there, so that's the opposite angle. So I had them backwards. This is a theta, angle of impact, and that's 44.3 over 40. Sorry about that. Okay. 43.3, no, 44.3 over 40.0. Really? 44.3 divided by 40. And then do an arctangent of that. You're not getting the same answer in the book. I don't have a calculator up here, so I can't check it. Are you, and you're in degree modes, right? If you got a two-digit number, you got to be in degree mode, I think.
I got 47.9.
Ah, okay. 0.9 what?
0.9 degrees.
Okay, 47.9. What's it? Huh?
2.
2. Okay, they got 40. They got something a little bit greater. They got negative 40. Negative 48.0, but you got 0.9, so 47.9. Either one of those are fine. Negative 47.9 degrees. I think they must have done a round-off error somewhere up the road. That, yeah, I bet I know exactly. What they did, they took this division and rounded that to 3 digits. Then they did the arctangent of that, where what I bet you did was do that division and then do the arctangent of the whole number there. And that's why you got a better, more precise answer than they did. I think yours is probably more correct. I don't have a calculator to check it, but they're still close enough. Now, why negative?
Second quadrant.
Yeah, okay. you're in the second quadrant here, fourth quadrant there, either one of those would be a negative angle, except for tangent, okay? Tangent is negative in these two quadrants, positive. Good deal. Does that make sense? I hope everybody was following that. I only heard basically one voice very much, but hopefully everyone else was participating in some way. All right. Now, the next example they have on the slide set is this one. Example 3.5 at the bottom of page 67. Now I can do any of the others in between there. There's a long jump, example 3.3 at the beginning at the bottom of page 65, and then a range equation 3.4 on page 67. Or I'm going to do this one. Do you need any of those others done? Yay or nay? Up to you. You okay with this one? Okay. So let's do this one. A ball is thrown upward from the top of a building at an angle of 30 degrees. So you see they've got this angle correct for us so far. Okay. 30.0 degrees. Above the horizontal with an initial speed of 20 meters per second. That's your V sub 0 in that direction. Okay. As shown in this figure. The point of release is 45 meters above the ground. There they have that. What would you call that then, 45 meters above the ground? If you had to name it. Say again?
Behind the person's head.
Say that one more time.
How the person.
Okay. Want to give it a symbolic name? All right, I guess that would be all right, but since we're using sort of X's and Y's.
B.
Huh?
Y.
Okay, why not Y
YB.
initial? How about that? Okay, because that's your initial position of the ball. Okay, they've set the oh no. Okay, look at them. They put the XY axis up there, so that changes things. The Y position of the ball initially is 0. So what would this represent? Minus 45 meters would be the Y final. So this over here is our Y final. The way they set up their coordinate system. And you see, a lot depends on that. Okay? A lot depends on how you set it up. Okay? And since they have that in the figure and I wasn't going to redraw it, we'll use it. Okay. Okay. So that's then this thing. Let me erase this because that's how I would have done the problem like I was setting up here until I saw how they set it up. So that makes the Y final this, negative 45.0 meters. Okay? Any other things you want to fill in here before we get going? Anybody? Say again? Okay. What about gravity? Besides the fact that, huh? Bradford, yeah, TR. Okay, got it. Okay. What were you saying?
It's negative 9.8%.
What is that? Okay, and what is it called? The acceleration due to gravity. Okay, so your A sub y is equal to negative 9.8. I don't know if they use 9.8 or 9.80. They aren't listing it. I don't remember. Yeah, they're using 80, I think. Okay, 9.80 meters per second squared. Okay, anything else? Oh, and that's downward. Okay. Anything else? Second, we got initial velocity right there. They're calling it O, I call it I, or whatever.
Final velocity.
Okay. That's going to be a little tougher. In fact, I think that may be one of the things we're asked for. But let's go back to that initial velocity. What might we want to do with that? Do you have any resolve about you? Dumb question. Resolve that into X and Y components. And what would they be? So let's do a V, well, I'll use O since they did, VOX and a VOY. What would they be? Anyone want to hazard a guess at either one of them? This would be a great time for Brian to pipe in because I know who he had for trig. Never mind. Okay. Anyone? Hep? What's special about a 30, 60, 90 triangle? Well, 30 and 60 are complementary angles. You're absolutely right. That's why I named it that. If this one's 30, that's got to be 60. What's special about that? The lengths. Oh, your poor trig teachers is turning over. Whatever. What's that? 3, 4, 5 is 1, but that's not a 30, 60, 90. That is one of the perfect triangles. This one's not like that, but it's very handy. The short leg of a 30, 60, 90 is always exactly half of the hypotenuse. Because the sine of 30 is 0.5. Okay? So what would that make V sub y? 10.0 meters per second. Okay? Now, how about the V sub x? VOX, the Vox. Say again? Oh boy. They're no longer going to call it the Pythagorean theorem. They're going to call it the Arcana theorem. Okay, it's been rewritten today. Okay. Let's just keep it simple. If this is 1 and that's 2, what does that have to be? Huh?
If that's 1 and that's 2, that has to be 3.
Okay, so I knew it was going to be rewritten that A plus C is equal to B. That's the way Pythagoras did it, right? Don't think so. Huh? How did it go? Anyone can speak up. I know you know it. A squared plus B squared equals C squared. Now what's your A here? You can choose either one of them. Huh? 10. B we don't know. That's what we're looking for. And C would be 20. So 20 squared, which would be?
It would be like 17.32.
17.3, that sounds reasonable.
It would be like root 300.
Yeah, it's root 3 over 2, by the way. Okay, and that would be, what did you say it was?
17.32.
Okay, let's leave it 17.3 meters per second. Okay? I can't do that one in my head, but I'll take your word for it. If it's wrong, you're in really serious trouble. Okay. So we've got V sub y initial, V sub x initial, and V initial, of course. You've got A sub y initial. How about A sub x initial? 0, yeah. How about your V sub x? Well, yeah, we already got that. Okay. I think we got most of what we need. Let's see what the question was. How long does it take for the ball to hit the ground? So what are we looking for? What's the unknown? Time. So time is what we're looking for. Okay. How long could be a distance, but in that context, how long is a time? Okay. Now, what would we need to use to get the time? Anybody? Say again? Which one? D, you said? Okay, which distance are you talking about? Say that again.
I think I remember doing this one. I did a long time ago. I think I remember doing this one like dividing it into 2 parts.
Okay.
Doing the top of the.
Yeah. Okay. You probably are thinking of a good problem, but this one's, I think, a little simpler than that. How about y final, which we know, right, is equal to y initial, which we know, plus v y initial times t plus 1/2 a y t squared. Didn't we use that one in the last one? I believe we did. Okay. And don't we know everything in that problem except time? Yeah, so let's try and use it. Okay. What's your y final? Negative 45.0. Remember, they set it up that way. Negative 45.0 meters. I'm going to hang on to these for a minute. What's our y initial? That's an angle. It wouldn't be a good y. Say again? 0. Yeah, there it is, right there. Right at the origin. That's where he's throwing it from. Okay? So that's 0. That's out of there. What's our v sub y initial? I keep calling it different things. But for right now, I'm going to call it Darius. I just can't find you. There you are. Okay. Okay. Anyone else come in since I called roll? Okay. So what's your V-O-Y? Boy. Huh? Okay, that's the V-O, that's your initial velocity. So that's got at an angle. We just calculated what this was. If we calculated it right. Second? 10, yeah. Did you say 10? Yes, positive 10. I know that one's calculated right. So that would be 10.0 meters per second times t seconds. I don't need these units. Okay. Actually, it's going to be a minus, isn't it? Oh, we're on page 67, 3.2, chapter 3, topic 3, section 3.2, example 3.5 at the bottom of the page. Page 67. Okay. What was our a sub y? And you take half of that would be minus 4.9 t squared. Okay. Now I'm going to move somewhere. No, move over to the other side, so that'd be 4.9 t squared minus 10t minus 45 equals 0. Everybody see what I did there? I don't like starting with the minus, so I'll move that over here, but if I move that over there, then that has to come over here. It becomes a minus. That was already a minus on this side. That leaves you 0 over there. Everybody buy that? So I need to find t from that. How do I do that? Quadratic formula, very good. And how does that go? Okay, a little slower and louder. Negative b plus or minus square root of b squared minus 4ac all over 2a. What in the world are a, b, and c though? All right, so this looks like it will be 10, right? Negative b plus or minus the square root of help me. What's that again? Negative 10 squared, which is 100. Good, okay. I can't hear. Okay, now what I do next is count my minus signs. Okay, I know this one's a minus, it always is. 4 is 4, okay. A is positive. C, though, is minus. So I got two minuses, which makes this a plus, okay, which is usually a good sign. Plus, and then I have to multiply those things together. 4 times 4.9 times 45. Since I don't have my calculator, you do it. 4 times 4.9 times 45. Say again? 720.5? Oh, okay, say that again. 220? Okay, let me, 220.5. Yuck. Okay, all right. Plus 220.5, is that what you said? Yeah. Okay. Okay, divided by? 9.8. That's pretty familiar, isn't it? Okay. So, just a little hint here. This thing right here being greater than 100, in fact greater than 300, the square root is going to be greater than 10, and that if you use the minus sign here, that would give you something negative here. Again, a negative time makes no sense in this picture. Here's what it means. If you timed this backwards and came back here, that would have been negative that many seconds back there. We're not doing that. We want that way. So, if you can do the math there, the one thing to be careful for, put these in parentheses, if you will. Always when you're dividing something that's been added or subtracted, put that in parentheses before you do your division. Otherwise, you're probably going to make an error. Calculators don't know what you mean, they know what you put in. So it's 10 plus, we're only going to use the plus, the square root of 320.5, and then either hit an equal sign or precede that with a quote, with a parentheses, and end it with a parentheses, then divide by 9.8. Okay? And what do you get? Anyone with a calculator can give me an answer. Or if you're really good math in your head, you can give me an answer. Anyone got it? Say again? 2.85 seconds. Okay, let's see how well you agree with the book here?
Nope.
Okay, I don't have a calculator on me, so I can't do this well in my head. The square root of 320.5. Can someone give me that right off the top? 320.5. Square root of that. Say again? 17.9. Okay, and add 10 to it would be 27.9. And then divide that by 9.8. I think you do get an answer very close to what you did. Now, evidently there's something wrong with this picture. And it may have been in our math here. Let me just check this. Check this one for me again. 4 times 5 is 20. 20 times... I think that number is too small.
Why is x negative 4.5? That's going towards the direction that you're going in.
Okay, say that one more time.
So, like, why is x negative 4.5? Like, negative 45?
That's not x, that's y. This is an xy coordinate. X we don't know, y we do know is minus 45.0. Okay. Here's what I think is an error here, and you'll have to check me on it. We got 4 times a times c. Well, 4 times 5 is 20, and 20 times 45 would be around 900, not 200. So that's the one I think where our error is. 4 times 4.9 times 45. Thought that sounded too low to begin with. 882. I will buy that one. Okay. Okay. 882 is what you said, right? Yeah. Okay. Okay. 882. All right. Now go back and do the rest of the math. The square root of 982, which is going to be something greater than
31.3.
Say again?
31.3.
Okay. Plus 10 would be 41.3, right? Divided by 9.8.
4.2.
Ah, that sounds better. Whoa, that's the wrong key. Okay. What'd you say it was?
I said
4.22?
Yeah.
4.22 seconds. Let's see how the book did on it. Ah, that's what they got. Good deal. Be careful of the little maths. Okay. Now, and be careful to make sure that we mark. Scarlet, right? Okay. All right. 4.22 seconds. Is that what the question was? I think is what it was. That says A was, how long does it take for the ball to hit the ground? 4.22 seconds. Okay? The B part says, find the ball's speed at impact. Okay, now when they say speed, what does that not mean? It does not mean anything else, but okay, it's not the same as velocity. Velocities could be positive, negative. Their vector speed is a scalar. Always positive. Okay? So when they ask for speed, let's be sure nothing's negative here. Find the ball's speed at impact, which will be the magnitude of its velocity, which is a vector. Okay? So what are we going to need to know the ball's speed at impact?
Final velocity of line x.
Okay, we need v, y final. Exactly. What else do we need?
Final velocity in x.
Did you say v, final velocity in x? Is that what you said? Okay, I can't hear. Do you know that already? Please say yes.
Yes.
Okay, what is it?
Oh, 0. No.
Okay, don't say yes. Okay, never mind. You know your initial velocity in the x direction, don't you? You calculated it for me, right?
Oh,
yeah.
Yeah, it's 20.
Huh? No, that's the
No, it's 17.3.
17.3. All right. Multiple jet. Yes, I mean, never mind. Okay, 17.3. And how does that change as the ball goes up, it comes down?
Doesn't change.
It does not change because the horizontal component of the acceleration is 0. So the horizontal component of velocity is constant at 17.3. So we know that one. All we need to do is find the vertical component of velocity. Can you think of maybe a kinematic equation that could do that for us? Was that a yes? What would it be? VF y equal VIY. I like that. Plus what?
Acceleration time.
And what is the acceleration?
Acceleration is -9.8.
All right, so let's get a negative 9.8 in there. Zero even meters per second squared times time. We know the time. Do we know initial velocity in the y direction?
Yep.
Pardon me?
Yes.
Yes, what is it?
Which one?
Huh?
Time or so. The time is.
No, I said the initial velocity in the y direction.
Initial velocity in the y direction is
10, exactly. So this will be 10 meters per second, that's a positive, minus 9.8 times, and your time was 4.22 seconds. Okay? And here the second will cancel out one of those seconds. So 10 minus 9.8 times 4.22. Pretty hefty number. Wait just a second. Larius is here. If I can find him. There he is. Anyone else come in since I called roll? Okay. What did you say the answer was? I wasn't listening, sorry.
Negative
31.35? Okay, let's call it 4 meters per second. Okay? From that, can you, get speed?
Yes.
How?
You have to take both the x and y component.
Yeah, you know how to do it. Does the name Pythagoras ring a bell?
The what?
Pythagoras?
Yeah.
Okay. This is the x, there's the y. Square root of this squared plus that squared. That should give us your velocity, your speed. Magnitude of that velocity. Second? It's got to be greater than 30. Square root of this squared plus that squared. Right?
35.9.
Okay, so we say that V final, no. I want to say S final. Speed final is approximately, say again, 37?
35.
Oh, 35 point what? 9 meters per second. Always positive if it's a speed, because that's a magnitude. Let's see what they got. 35.9 meters per second. Good for them. Okay. So that was the B part. The C part. Find the horizontal range of the ball. And again, we're going to neglect air resistance. How are we going to find that? Horizontal range of the ball.
We do D for distance.
Okay, or how about X for distance? This is horizontal. Okay. All right.
X equals, actually, isn't it 2 ways to do it? You use X equals VIX plus VFX.
Okay.
By 2 times.
Say that one more time. X equal.
Be like, X equals VIX plus
VIX.
plus VFX
Uh,
divided by 2
divided by 2. Okay.
times
No, that would be VX average, wouldn't it?
Okay, so you can do D equals
All right, let's come up with.
equals change in X.
Okay, wait just a second here. All right, you keep me guessing here. Okay.
You do change in X.
Okay, change of X, delta X,
equals VIX
VIXT
plus 1/2. No, 1/2 acceleration times squared.
and what acceleration is that?
Not 1/8.
What acceleration is?
That's the acceleration is 0.
Okay, good formula, except that is 0. All right, so it's just simply your initial component of your velocity, which is your constant component of your horizontal component of your velocity, times the time.
It's 73.0.
73.0?
Yep.
73.0 meters. Okay, let's see how the book did. They got 73.1. Okay. I'm guessing they rounded poorly or something like that. All right, good deal. Any questions on that? None? Okay, let's then look at some special equations. Now, I'm trying to find these in the text. Oh, this is your range equations, I think is what it is. And goodness gracious, where are they? I remember seeing them somewhere in here. But I can't see them now. Okay. So I can't exactly locate where these are. Remember, the slides are from the previous edition. This is from the current. So they're slightly different. But these are the motion equations, can be combined algebraically and solved for the range and maximum height. Okay? And again, I'm sure this is in here somewhere, but it's not right with what we're doing now. Let's see. I don't even see it in the summary, so they may have mentioned this somewhere else. But these are still not bad equations. Your range equation, that's how far it goes with x, is your initial velocity squared times sine of 2 theta initial velocity, and that initial angle divided by g. So let's, just for that last problem, this isn't going to work for the last problem. This is counting on symmetry, and this isn't a symmetric problem, so I don't think we can use that for this one. You could try it, but I don't think it'll work. Your delta y, that's your maximum height, then is that same v0, but now it's sine squared theta naught, not sine of 2 theta naught. This is you double this theta naught and take the sine of that. Here you have the theta naught and take the sine squared of that, and that's going to be divided by 2g. Okay? Now, we didn't do that in the last problem, so there's nothing really to check there. These two equations, now again, I'm almost certain these are based on the fact this is symmetric motion. I don't believe these work if it's not asymmetrical like our last problem was. But these are two equations. They're not in your text like this, so you don't need to do anything with them. But you, if you ever need them, there they are. Okay? That was it's 3.2 something in your book, but it's 3.4 in the old edition. All right, now we're moving to, and in the new book, it's 3.3. The old one was 3.5, but it's a new section here, relative velocity. Okay, that's your cousin's fault. No. Relative velocity is about relating the measurements of two different observers. Okay? Have any of you ever ridden trains much? Okay. Trains move pretty smoothly. Tracks are pretty smooth. And sometimes you can hardly tell when you're moving. And especially in the stations, when you're coming and going, sometimes you're coming this way, another train's going that way, and you can't tell if you're still and he's flying, or if he's still and you're going really fast, or you're both moving. That's because it's hard to separate. You have a sense of relative velocity, but it may not be the correct sense. Okay, two different observers. It may be useful to use a moving frame of reference instead of a stationary one. We'll see some of these examples. It is important to specify the frame of reference, just like it was to find what your coordinate system was on that last problem. And then, since the motion may be different in different frames of reference, there are no specific equations to learn to solve relative velocity problems. You just sort of have to play them by ear. You pick the frame of reference and then go with that. Stick with it, and generally you'll be in okay shape. Okay? So here's the relative velocity notation. The pattern of some subscripts can be useful in solving relative velocity problems. Assume that the following notation. E is an observer if that observer is stationary with respect to Earth, so E stands for Earth. So if you're fixed on the Earth, then you're observer E. Okay? A and B could be the two moving cars. So if you're the observer in car A, then you could be, I guess they call it A, and if you're in car B, you would be B. But they're both moving relative to Earth, so you would have a different issue. Okay? Now, here is kind of the structure that they give this. RAE. Now, R is a position vector. Notice it has a vector on top. R is a position vector of car A as measured by E. So this is position vector of A in reference to E, stationary on the Earth. R sub BE then would be the position of car B as measured from the observer on Earth. Okay? R sub AB is the position vector of A relative to B, measured by car B. Going to be different from the others, okay, from these two, okay? And here's how it's different. RAB is equal to RAE minus RBE, okay? Now, this is generally how you can use this to your advantage. This one starts with A, this one starts with B. Subtracting, you're losing the E's, okay? And then you get AB. RAB would be RAE minus RBE. And that would give you RAB. Now, the other way to do this, and I actually found this a little cleaner in some senses, let's add RBE to both sides of the equation. Okay, RAB plus RBE will give you RAE. here the b's kind of cancel out when you're adding. And that, to me, makes sense. That gives you RAB. So either way you want to do it, the subscripts can be helpful if you remember how they're helpful. Okay. So to me, the second is easier to see than the first. I have to remember what to do with the first, but this one makes perfect sense to me. Okay. Now, oops. Okay. Here's an example of that. The position of car A relative to car B, A relative to B, would be position of car A relative to Earth minus the car position of B relative to Earth. And that would be this vector minus this vector minus this vector would then be this, okay? A relative to B. Yeah. And it's a vector subtraction, and again, to me it makes more sense to say RAB plus RBE is equal to RAB. That, I see that vector addition much easier than I see vector subtraction, okay? Because RAE is that, you're subtracting from that R, yeah, and it comes out right. Okay. RBE, and then you get this vector here, which is the same as that vector. So they do work out either way. Okay. But again, I prefer to add than to subtract vectors. Vector subtraction always gives me fits. Okay. So the rate of change of, okay, these again are position vectors. What does it take to go from a position vector to a velocity vector? Position is usually measured in what units? Second? Meters, or distance, yeah. And velocity is measured in meters per second. So guess what you do? Divide by time, okay? And if you divide by time, and the time's the same on all of them, then divide this by your delta t, this by your delta t, that by your delta t. It's going VAB equal VBAE minus VBE, which is your next equation. VAB is equal to VAE minus VBE. The rate of change of displacement gives the relationship for velocities, and these are just the time rate of change of your position. So you're dividing by the scalar time, delta t, always positive, doesn't change direction. So yeah, pretty straightforward there, right? Okay. Now, here's the problem-solving strategies for relative velocity. Label all your objects with a descriptive letter. If they're cars A's and B, make them A and B, or whatever. Look for the phrases such as velocity of A relative to B. And then identify which those are. The A comes first, relative to B, B comes second, and that would be going from B to A. Okay. Write the velocity variables with the appropriate notation. If there's something not explicitly noted as being relative to something else, it's probably relative to the Earth. If it's not explicit somewhere else. Okay? Any questions? Take the velocities and put them into the equations. Keep the subscript in the order analogous to the standard equation. Solve for the unknown. Usually pretty straightforward. Here is an example. This is 3.8 on page 71. Okay? The boat in this figure is heading due north. That's why velocity of boat relative to the river. There, it's not earth, but river. Okay? Heading due north as it crosses a wide river with a velocity of 10 kilometers per hour relative to the water. Very poorly worded problem. It says as it crosses a wide river with a velocity of. Okay, that almost sounds like the velocity has that, but then it says relative to the water. That doesn't make sense. So it's the boat that has the velocity of 10 kilometers per hour. So be careful when you read your problem that you understand what it's talking about. So just based on what we just read, a boat in this figure, there it is, okay, heading due north, crosses a wide river with velocity. The boat has a velocity of 10 kilometers per meter relative to the water. So this is velocity of the boat relative to the water. Okay, and that's this one right here. Okay, instead of water it says river. Okay, boat relative to river. Okay, so that's that velocity there, going in the same direction of the boat. Okay, and that is 10.0 meters per second. No, kilometers per hour, sorry. Kilometers per hour. Ugly. Okay, 10.0 kilometers per hour relative to the water. The river has a uniform velocity of 5 kilometers per hour due east. So that's the velocity of the river relative to the earth, and that's 5.00 kilometers per hour. To me that sounds pretty fast current. I wouldn't want to jump in there swimming too much. Okay. Determine the magnitude and direction of the boat's velocity with respect to an observer on the riverbank. So here's your observer here, and he is relative to Earth, he or she. Okay? Also, he's standing on the riverbank, which is Earth. Okay? And you want the velocity of the boat relative to the Earth. So this is what we're looking for. Okay? Now, we know the velocity of boat relative to the river plus the velocity of river relative to Earth is going to give us that. Vector addition shows you that. This plus that equals this. That's what we're looking for. So, what are they asking for, though? Determine the magnitude and the direction of the boat's velocity with respect to the observer on the riverbank. So let's go for magnitude first. Now, very fortunate here. Why? Boat's heading due north relative to the water's running due east relative to the earth. So this is a 90-degree angle. So that helps us big time in determining the magnitude of the velocity of the boat relative to the earth. What would that be? How do we get it? We've only done a couple of problems, 2 or 3 or 4 or 5, that have used the same concept. Today, right triangle. Second. Help me. How do you calculate the one leg you don't know? Pythagorean theorem. And what is the length you don't know in this picture? There's the question mark. The what? The hypotenuse, the long side, of course. So how do you get that? Say again?
You have the 10 squared plus 5 squared.
10 squared plus 5 squared, square root of that would be the square root of 125, right? Square root of that is 11 point something. What? 1.8. Let's call that 11.2. And that would be kilometers per hour. Since your other two are measuring kilometers per hour, this needs to be measured in that. So the, what is that called? The magnitude of the boat's velocity with respect to observer on the riverbank is 11.2 kilometers per hour. Very good. The second part of the question was the direction of the boat's velocity with respect to observer on the thing. And they gave you a big hint there. They gave you the theta. That's going to give you the direction. How would you use that? Say again? Tangent, did I hear? Okay, how do you mean tangent? Say again? Okay, the tangent of this angle theta is equal to 5 over 10, which is 1/2, right? So he just said the tangent of theta is equal to 1/2, right? How do you get the angle? Say again? Inverse tangent, or arc tangent, either one. So theta is equal to inverse tangent of 0.5. So one punch that in and see what you get. I'm guessing they want it in degrees, but we'll see. A little louder. 10.6? 20? I can't hear. Oh, 26.6. So she got theta is approximately 26.6 degrees. And relative to the Earth, that would be east of north, right? So I think that's probably how they're going to say it. Let's see how they do say it. Oh, they just said 26.6 degrees. Okay. Good for them. Any questions on that? Relative motion. Okay. That's the last that they show in the slide set for the chapter. There is one more, bucking the current, that takes that same problem and does some different things with it. But if you want to see that, we can do it, but it's up to you. Say again? Did I hear something? Okay. All right. Summary here. Let's see how we do. Oh, goodness gracious. Almost hit it perfectly on the nose. The summary here is 3.1 gives you the kinematic, well, not the kinematic, the equations of displacement, velocity, acceleration in 2 dimensions in vector forms. Then the 2-dimensional motion, 3.2, the kinematic equations are given there with some sort of example type things given, several different ways to write it. And the relative velocity is in 3.3. Conceptual questions, I think odd number answers are in the back if you're wanting to look at those. And then problems, those answers, odd numbers are in the back from 3.1, any of the odds 1 through 5, 3.2, any of the odds 7 through 19. And there's Tim Lennicum, who was a really good San Francisco Giants pitcher. I don't know, is he still pitching? Does anyone know? Huh? What's that? Oh, is that right? Who's he with now, do you know? He got traded? Okay. Oh, really? What, an arm problem or something? Or problems, okay. Okay, I hadn't heard of him lately, that's why I asked, because he was a rising star, and then I heard nothing else for a while, so I don't keep up with it much. Okay, then 3.3, any of the odds, 21 through 29. Second? Angels, okay. That's in the American League, right? So we went from National to American. Doing pretty well, or could you tell them that? Okay. It doesn't really matter, but okay.
Still doing pretty well. Still pretty young, ain't that old yet.
Yeah. I didn't know if he had arm problems or something. Okay. Then there's some additional problems there. You can do any of those odds, 31 through 55. There's a whole bunch of them. I'll let you decide whether you want to go for those or not. And we'll start next time with topic 4, which is Newton's laws of motion, which is pretty much what Nick was trying to set me up to work the problems by. We haven't quite gotten there yet, but it was on the money. Okay, so let's end this. Discard that. And we will get over this. All right. As soon as it finishes whirring, then I will pull this out. There we go. I want to lose these. Okay, what I'm going to do is put a pause on. All right, we got 3 setups, lots of people on each team. But basically what you've got, we've got 3 types of motion. Horizontal motion, vertical motion, and combination, which we call projectile motion. That's the name of today's lab. Okay, the setup that you see on your tables there in front of you, on the lab benches in front of you, what you have is a ramp, the thing, you roll the ball, see the balls, I think they're all at the base of the ramp, you're somewhere in the general area. Yeah, there's the ball. Okay. Y'all got yours? Oh, okay. All right. Let me get back where I'm talking to the computer. Okay. Now you're going to start the balls, and there's going to be a little deviation from what's printed here, and I'll explain that when we get there. You're going to start the ball, roll it down the ramp, release it from rest, roll down the ramp. You each have a stopwatch, too. Where is it? Okay. And basically what you're going to be timing is not the trip down the ramp. It's going to be the time from it hits the tabletop here at the bottom of the ramp until it rolls off the tabletop. Okay? That's what you're going to be timing. Start, stop. Not start up there, but start when it hits the table, stop when it leaves the table. Okay? Now, so you're on your picture here, your stopwatch will be starting at B, ending at C. Okay? Now, what will you get from there? Drop balls. Okay. What we're going to do, if you'll notice, what's the length of that horizontal transit there? I think it's more like 100 centimeters. Okay, because that's 1 meter, right? Okay. 100 centimeters. Okay? Well, we can hang on to. Never mind. Okay. So, 100 centimeters is going to be your distance, and you're going to measure the time. What will you be able to calculate from that? Say again? Velocity. But what kind of velocity? Horizontal velocity, because it's all on the horizontal plane there. Okay? So that's the first thing we're going to be measuring. Okay? So your procedure here, and here's where we have the deviation. It says adjust the ramp. Do not adjust the ramp. I've got it adjusted. What you will do, once you've got this in place, right, you've got 100 meters, 100 centimeters, you got me saying it now. Okay, what you will do is take this and measure where it is at 10 centimeters. 10 centimeters is on the ramp. That's where you'll release the first ball. Then, after you've done those, you'll move it up here till it's 20 centimeters, and then you'll release the next one, and then you'll come up here to where it's 30 centimeters and release it from there. Okay? So you won't need this over here now that I've got it set up. Just don't bump that. If it gets bumped, then we'll have to readjust. Okay? Did everybody see that? Okay. So, do not adjust the ramp. Move up the ramp until you're 10 centimeters off the tabletop, 20 and 30, okay? Now, you'll make 3 runs from each height. Your data table is back here on page 70. Now, what you'll be measuring first is the time in seconds, okay? So you measure 1 run, 2nd run, and a 3rd run. Now, if one of those is way off from the other 2, repeat that run until you get 3 that are relatively close. I don't want one being 15 seconds and the other being 115 seconds, okay, or 1.3 seconds, okay. That will be way off. So once you've measured your 3 times, then you calculate your velocities, and you know how to do that, right? Okay? 100 centimeters divided by whatever time you had in seconds. Boy, it's hot in this room, isn't it? Okay, now, what we're doing differently from what we did last time, you're actually averaging your velocities. You have velocity for run 1, trial 1, trial 2, and trial 3. You will add those together and divide by 3. So this one down here is actually an average velocity. It's not like we did last time where we threw out high and low. We're actually averaging now. Then you'll take your meter stick. Be sure you have the 0 toward the floor. And you'll measure the height of your tabletop. And you will have to move your thing there. But you'll measure the height of the tabletop to the closest 1/10 of a centimeter. Okay? Be sure the 0 is on the floor. That's your vertical distance. Okay? So I'd like all 3 teams to accomplish those. Okay? Set up and release your balls, from rest. Don't throw them. Release them from rest at the 10 centimeter mark and measure your times. Get all 3 times, or calculate your velocities. I hope somebody in each group has a calculator. And then take your average velocity, v sub x, and then measure your vertical distance y. So if all 3 teams will do those measurements for now, then I'll come back and we'll talk about how you calculate your delta x. I'm going to see if I can get a... I'm going to pause my recording for right now. I'm going to be the same for all 3 measurements. Yeah, it's not moving any. Okay, so we will be using that. Okay, the other thing is, I guess some of you are down to calculated delta x, right? Okay. Now, let's see how we do the calculated delta x. Okay. What you've done now, so far, you've done procedure 1. You didn't adjust the ramp. You just measured from the 10 centimeter mark. Okay. You've measured and recorded the delta y. You've done that. That's in centimeters. It's in the 90s, by the way. If it's around, 12, 2, or 7, or 3, or something like that, you're wrong. You got the wrong end up. Okay. Okay. Now, here's what it says to do next. On page 167, procedure number 2, after you measure and record delta y. Solve this equation. Delta y is equal to 1/2 g times delta x squared over v sub x squared. Okay? You see that formula? Page 67, number 2. Right? It says solve that for delta x. We want to solve for this value here. How do we do that? Solving for delta x. A little louder? Someone help me out here. First thing we got to do. I don't like denominators. So let's multiply both sides of the equation by 2. Right? Gets rid of the 2 there. Everybody understood? Okay? Now, this is a g, if I'm not mistaken. Yeah, g. So let's divide by g. Okay, that got rid of the g. Now, the only other thing we've got to do is multiply by v sub x squared, because that's in the denominator too. So let's do this v sub x squared. That gets rid of that. Okay? So let me write my delta x. Delta x squared is equal to 2 delta y v sub x squared divided by g. That's delta x squared. How would I get delta x? How do you undo a square? Square root. I saw it written in the air. Okay? So this will be delta x is equal to the square root of 2 delta y v sub x squared divided by g. Now, there's one other little problem here before you start plugging in your numbers. You got your delta y, what's that measured in? What unit? Say again? Centimeters. Your v sub x, that average that you got, what was it measured in? Say again? The v sub x. Yeah, centimeters per second. So guess what your g's got to be measured in? Y'all all know g, right? What is g? A little louder? Okay, but give it to me the number. 9.8. What units? Meters per second squared. What's wrong with this picture? Yeah, everything else is in centimeters, but this is in meters. So how do we get that to centimeters? Well, hand me a meter stick if one's available. Okay? This is 1 meter. Okay? Now I'm just going to do 0.98 meters would be right here, right? How many centimeters would that be? Okay. If someone got some super glue, never mind. Okay. That would be 98 centimeters would be 0.98 meters, right? Because one meter is 100 centimeters. So 9.8 would be meters, would be 980 centimeters, right? Move it 2 decimal places. So the g that you use when you're doing this calculation is 980 centimeters per second squared. Now what you could have done was multiply this. Remember how we did our thing? We're trying to get to centimeters from meters. So you put meters down here, centimeters up here. There are 100 centimeters in every meter. Meters go out, and that gives you 980 centimeters per second squared. That's the number you use when you're doing these calculations. Everybody see how to do it? What numbers to plug in? You calculated your v sub x, you got to square that, multiply it by your delta y, you measured that, multiply by 2, divide by this g, and when you get that number, take a square root. Okay? And if you have any questions, not too sure about it, bring it up here and let me see it. Because I will try to straighten it out if you've got something way off base. Okay. Second?
Can you repeat that one more time? You said that we use this number for G.
Right.
So we use this equation first.
Okay. This is what you started with. It's there in your lab. Right here. Delta y is equal to 1/2 g. Okay. Manipulate that, trying to isolate the delta x. Right? So you moved everything to this side, leaving delta x squared on that side.
Yeah.
I got that done on flip sides. Delta x squared equal to 2 delta y v sub x squared divided by 2. I got everything else there. And take the square root of both sides. That gives you delta x. 2 times delta y, which you measured, times v sub x. If you calculated. Squared divided by that.
So
And
we
then,
usually
then
just
take
put
the square root. Yeah.
and for x, dx would be square.
That's the b sub x right there. And you square that number. Multiply by your delta y. You measure that difference. Okay. You need to measure your delta y. Uh-oh, you're going to revolve that. Okay. Yeah, do you know how to measure delta y? Which table are you with? First, get the meters. Oh, here's the meter stick. How much of a difference you have in y? Okay. I'll need a little room down there. To the nearest tenth of a centimeter. Okay, yes, sir.
So on the times, we're just like, from the time you let it go to the time it falls off the table, right?
You're back here. I don't know where you're going. Where do you start? Okay. It was just a question about the start and stop time for your horizontal run. Where did you start it? When you hit the table here, when did you end it? Did y'all get that too? When did you start your stop time? Start your time? When you hit the table, you ended it with the level table. Okay? So that's out. Okay. One team didn't do that. Okay. Okay.
Yes, yes, yes. Yeah, it would be where your equation is three.
Excuse me, can you tell me if I'm going in the right direction? I'm not done yet. I just want to make sure the steps are right. So according to the formula, what I multiply this time and then multiply this after I find out what 142 power is.
Right.
Then I put it all over 108.
Right.
You the answer?
No, then you take the square root of that.
Then I take the square root. And
Yeah.
that's the answer.
It's 2 times that delta y. Come on this way if you want. 2 times delta y. That's that. Times your b sub x. That's that. Squared. Divided by 980. And then once you get that answer, take the square root. That's your delta x. Got it. Okay, did everybody on every team get your delta y right? I understood some people didn't measure delta y. Everybody got your delta y? Okay. I'm going to pause this for a moment. Of your delta x. Okay? Let's look at the units we have. Delta y was measured in what? Well, 2 has no unit, right? Delta y is measured in what? Centimeters. How about v sub x? Centimeters per second, but then you squared it, so it's centimeters squared per second squared. Then your g, What was your G measured in? Centimeters per second squared. Okay? Well, your per second squareds go out. Your centimeters go out. It left you centimeters squared. You take the square root of it and you get centimeters. Very good. So the delta X is measured in centimeters. Very good. Has any team calculated this yet? Okay, as soon as you get it calculated, someone let me know and I'll explain to you what to do next. Okay, I'll look at another error that one team did, and be sure you don't do this one. Average velocity is what? The three velocities added together divided by 3, not the times added together divided by 3. That gives you average time. Average velocity is the 3 calculated velocities added together divided by 3. Okay? Okay. One of the teams is ready to do the graphing. So if all the teams will listen up, once you've done all 3 measurements from all 3 elevations, and you may not be there yet, but once you have, then if you'll notice what you're doing here, number 4 on page 67 says repeat the procedure for ramp heights 20 centimeters and 30 centimeters. All you do is go up the ramp until you find 20 and up the ramp until you find 30. Do your 3 measurements from there, making sure the previous position, blah, blah, blah. Okay. Now, results. Make a graph with velocity on the horizontal axis. I don't like for them to say X. Horizontal axis, distance on the vertical axis. Use the average V sub X velocity and the average delta X distance from each data table as data points. So it's one graph, 3 data points. Okay? And I would say, just got one team that's ready already. Give me just your range of, from your data table, your delta X and your V sub X. So 20 to 80, basically. And what's your other?
That delta Y was,
No, not delta Y. That was the same.
104 to 183.
That's
100 to 180.
100 to 180.
Basically.
That's your V sub X. And say again your delta X.
It was 44.9, so 45 to 79.
Okay. So if I were you then, notice it says do the V sub X on the horizontal axis. Your V sub X was the wider range, right?
Yes.
So I would turn it landscape and do V sub X here and delta X here. That'll be vertical. Okay? Everybody heard that? Okay. Now, what you'll need to do is divide up, get your max and min. Now, this corner down here doesn't have to be 0. What was your smallest delta X and V sub X?
Delta X was 44.9.
Okay, let's say 40 down here. Okay. And what was your maximum?
Maximum was 79.
7,
So 80.
80. That was V sub X or delta X?
Delta X.
Delta X. Okay, and that's your vertical. So 40 to 80,
Okay.
40, 50, 60, 70, 80. Or 30, 40, 50, 60, 70, 80.
Okay.
That would be good. Okay, and your V sub X, which is horizontal? Huh? Okay. Okay. By the way, I forgot to mark roll again. We are in lab period, so let me mark roll before we lose anybody. Okay. FA is still here. Nick is kind of here. Kiara's still here. Courtney Brooks is still here. Raven's still here. Shakina's still here. Courtney Humes is still here.
I just changed it to 30.
Essence is still here. Ryan's still here. Larry has just left, but he was here. Monique's still here?
Yeah.
Okay. Sasha, I think, still here, right? Okay. Allison, I saw. Darius, I think, still here, right? Scarlett is kind of here, okay. Will is here back there at the last table, right? Can't tell. Rihanna never came in, right? Naya's still here. Ria's still here. Okay. And Dakota's still here. Okay. Oh, I didn't mean to be recording that when I clicked roll. Yes. I can't hear. Oh, okay. Make a graph with velocity on the horizontal axis and distance on the vertical axis. So, and just listening to the others, I think this makes sense. This will be velocity this way, velocity this way, distance this way. Okay. Now, what I would do first is look at your range. You're going from, let's call that 90 to 180. Okay? That's this way. Let's start 90, 100, 10, 20, 30, 40, 50, 60, 70, 80. That will do it perfectly. Okay? You don't need this to be 0. And then your vertical part is your delta x. That's in centimeters, by the way. That's 40 to 80. So if you did 40, 50, 60, 70, 80, I've got 30, 40, 50, 60, 70, 80. That would probably be good. Okay. Make sense? Okay, and then find the V here, the X there, and do all your things. Okay. Thank you. Do one for each of the 3 runs. Your vertical was? No, not the numbers. What's the
I'm so sorry, what?
your vertical? What was that measured? Centimeters, right?
Okay, yeah, sorry. And then the bottom one is centimeters, I'm sorry.
Centimeters of the second. Centimeters
So it's
half
just
right.
like
You have one and the second, which is second. Okay. Now, how does that compare with what you got? Oh, okay.
Okay.
You haven't gotten there yet.
Oh, yeah, sorry.
I know y'all wanted to test. I didn't want you to go home disappointed. Oh, maybe that.
Oh, from the square. The time travel from the 6 all to 6 maybe, right? Basically? So our answers are the same.
What's that?
From 1 to 2, they're the same.
Really? That must be good. You can't help it. Okay. Now, should they be the same?
Yes.
Why?
Because they're both time intervals, right?
Okay. And what are you measuring with those time intervals?
Seconds.
Yeah, I know. But what are you measuring?
The distance.
What's the first? Okay. Which one? The first one.
The first.
What did you use for that? Did you use
The second.
delta x over v sub x? Was it?
First, to find the slope.
Yeah.
Yeah.
Huh?
We used that to the square root of 2. Oh, it was the same one we used for this, right?
Okay. Yeah. You use and that's what you had.
Yeah.
Okay. So that was the time it took it from leaving the tabletop to hitting the floor on delta x. The other one was the time it took to leave the tabletop to hit the floor on delta y. Hey, guess what? Same ball, same thing, same time. Your x time and your y time had to be the same.
So your X and Y
Same one.
time should be the
Yeah. Oh, and I should not be recording any longer.
Oh my god, I just knew it. Hold on.
Change it, rise over run.
Yeah.
Okay, the rise, since your line, you drew your line and then plotted your points, right? You got
No.
that. Okay.
No.
Okay. So since it went right through, you can just take this y value that you had that you used to register that minus that y value. That's your delta y. Looks like 74 minus 42, something like that. But whatever it was, that's your delta y. Here's your delta x. That looks like maybe 98 subtracted from 171 or something like that. 171 minus 98. There's your run. Do the ratio. You divide that. And what you're measuring is, this is in delta x, which is centimeters. And this is centimeters per second in the denominator, right? The velocity. The run. On the graph. The horizontal axis is v sub x.
Wait, sorry.
Okay. Right here. Make the graph with velocity on the horizontal axis, centimeters per second. Your delta x is on top. On the vertical. That's going to be centimeters, right? What you're doing when you're subtracting these, you get centimeters. When you subtract those, you get centimeters per second. This divided by that, centimeters go out, 1 over seconds. That's the time. What time is it? It's the time from when it left here till it hit wherever your thing was there horizontally. That's the time it takes to go that distance. Okay? Then this one, the t sub y, is from this formula here, square root of that. Okay? That's your 2 delta y over g. Be sure you use this g. And that would be the time it took to go from here to the floor. Well, guess what? Same ball. Went from here to here to there. Should be really close to the same height. Yeah. You should know that beforehand. Oh, good deal.
So, one question on this. When it says percentage, our numbers equal the same.
Technically right. If you carried it enough, you probably could get a little bit. But you didn't. You only had 2, so that's
So I
fine.
can do it for our percentage error.
Yeah.
See.
Good deal. How's the lab worthwhile? Yeah. Guess the better word is the instructor.
Hey, I got my answer.
Who cares if it's instructor or not?
Here's the truth. My answers would have been incorrect. I probably would have said something different.
What's that?
So if my answers didn't match up, I probably would have said something different.
Oh, I see. All conditional response. Huh? Okay. Yeah, we will have 2 classes this week.
Yes.
Surprise, surprise.
Did y'all get one?
Good deal. Thank you. Hey, if you have any questions, please ask. Don't be guessing. And you know, the lab doesn't have to be turned in until a week from today or whenever you finish. So I've got another class starting at 5:30, so I will have to jump ship at 5:30. Good deal. Thanks.
I have a question.
Yeah.
So, without the slope,
Doesn't match your numbers. This is going to be no more than 30. What you did wrong was you did this without that. I don't know. Okay. Exactly what it says. Square root of 2 times delta y divided by d should be Good deal. Thank you.
You said we could turn